Welcome to this recording. Hope your semester's going well. And we're going to talk about numerical differentiation, and the same techniques would be applied to numerical integration. But mostly we're going to talk about differentiation today. And we're going to do Richardson's extrapolation, but that's going to be usually something we're going to do based off of an integration problem. Either way, we're going to go back to just Taylor polynomials. So let's first, before we do that, let's just go back to the definition of the derivative. So if we're talking about numerical differentiation, what's the first thing we're going to want to try? Pause the video and try to remember the rest of this. Okay, what is this? Hopefully you're going to tell me f of x plus h minus f of x all over what? H. Or if you used a delta x, that's the same. I don't like delta x's because it just takes more time to write. Okay, let's do it. So there's a name for when we do this. It's called the forward difference and backwards difference formula. Forward difference. We call it forward difference when we're taking the derivative based on exactly what this says. And we call it backwards difference when we're stepping backwards, but it's exactly mathematically the same, but you just use it going backwards. I'm sure you did stuff like this in calculus. These guys, so in this case, let's say h is greater than 0, otherwise these wouldn't be different, right? These are the official, in other words the only, 2-point formulas. And I'll explain that in a second. So in the homework, there's a time when I say use a 2-point formula in quotes, and I say you're allowed to cheat. And the reason for this is, okay, any reasonable person, if you're given the option to find the derivative here, if you have h plus, I'm sorry, I put h there instead of x. Good grief. Here's x plus h, x minus h. Any reasonable person would actually use these 2 points. This is a totally valid numerical technique, but it's considered to be a 3-point formula. But no rational person, when trying to find the derivative between x, at the derivative at x, no reasonable person would use forward or difference if they had the option of using the midpoint method. Okay, so I'm going to allow that, even though this is a 3-point method. It only uses 2 input points. So anyway, that's what I mean. And so this formula, here's what it will look like. F prime is approximately equal to f of x plus h minus f of x minus h. Figure out what the denominator is. Please pause the video and think about that. Tell me what the denominator is. Hopefully you said 2h. Okay. Alright, so even though that's a 3-point formula, it only takes 2 input points. Alright. What about error terms? Errors on these guys. Okay, so f of x plus h is, using Taylor, approximately f of x plus f prime of x times h plus f double prime of c h squared over 2. Okay, so you remember what this means. If you've got an f, here's f at x, and we have a whole bunch of information at x, and the place where you're going to actually approximate it somewhere later on h is going to be somewhere over here, then the c has to be somewhere here between the starting point of your Taylor polynomial and the endpoint of where you're calculating it, that means there's a c somewhere in that range that makes all this work out. Okay, so if we just do a little bit of algebra here, we can get back to our technique. What a mess. I always forget about those crazy denominators. Okay. Then I'm going to just divide everything off by h. Hope you don't mind. Right. I just don't want to write this again. Alright, so this is what we get. Okay, so this is the order of the error, or this is the error term, so it's going to be order of h. On the order of h is where the error is. I'm not going to worry right now at this moment about exactly how big f double prime over 2 is, okay, but the h is significant, and that this kind of analysis is telling us the speed at which this thing is converging or not really converging, because this isn't iterative. It's just telling us how accurate it is on one round. Okay. So generally it's more annoying to find error bounds, but this is pretty straightforward for this question. Okay, here's a question. Find a coefficient to maximize accuracy in a 3-point formula. Okay, so these kind of questions are sort of the baseline of this chapter, and we're going to be doing these kind of things a lot in this course, so I'm going to pause to just set up the question. Okay, so what we have is not much information, but it means we have equally spaced points on x, and so we've sampled a function in 3 places. Okay, you could have written x minus h, f of x minus h, and so forth. You could have put that x in the middle, but it's what we're doing right now is we're just putting it on the left hand side. Okay, so here's how you work this problem. You first, I'm leaving some space because I'm going to put something up there, but I'm going to just say f of x plus h and f of x plus 2h have to be expanded using your Taylor techniques. Again, I'm using a little space around there. If you're taking notes, you might want to wait till this discussion is over and then go back and copy the notes. That would probably be a good technique. So you're going to do f of x plus f prime of x times h plus f double prime of x h squared over 2, and then you're going to have some kind of error term, but let's pretend like we can be hopeful. I'm going to turn this piece into a c later, but just in case I can actually satisfy this point, satisfy this out to this level, I'm just going to leave it like that. I'm going to leave it like that, and later if I want I can turn that h into a c. I'm going to do the same thing down here. This time I get it 2 times h, and instead of h, and then instead of h squared I'm going to square 2h, so it's going to be 4h squared divided by 2, so it's still going to be a 2, ironically. And now I'm going to get an 8 coming out, so it's an 8 over 6. I'm going to leave it as 8 over 6, but okay. And I know in advance that I'm not going to end up using that term, but anyway, so the point is, what I really want is f prime of x is going to be some linear combination of this, a times f of x plus b times f prime of x. I mean, sorry, I meant to say x plus h. Here we go. Plus c times f of x plus 2h. So our goal here is really just to find the coefficients. That's why I only expect to be able to solve this many conditions, because you usually go out to h squared when you have 3 coefficients. That's not always true, but let's think of this. F of x equals f of x. That sounds stupid, but if you have a copies of f of x, you only have a copies of f of x. But now, with b and c, it gets more interesting. B copies of f plus h. I'm going to just expand this. I'm going to stick a b in front of each of these terms. And the same thing with c. So the deal is, if I'm going to add up a f of x plus b, f of x plus h plus c, f of x plus 2h, I want to get all these coefficients to balance out. I would like to write them correctly too. So now I want you to think in terms of columns. Okay, so this is our technique right here. This is our technique. Now we want to find a, b, and c to make the technique as good as possible. Now, we could do this for anything. We could do this for looking for f double prime or f triple prime. But the goal here is to find f prime. So we want b plus c to be chosen. In fact, b plus 2c. So the condition on b plus 2c should be 1 over h. b plus 2c over, it should be 1 over h, because we want to also make the h's disappear in this case. So if we can get b plus 2c to be 1 over h, that would be great for us, right? But that means a plus b plus c has to equal 0, because we want these terms to all disappear. This, we want the leftovers to just be f prime of x. Okay? And so because we're trying to approximate f prime, there's going to be an h somewhere in this expression. There's not going to be an h anywhere else, because nobody else cares what h is. Over here, we need to make b plus b over 2 plus 2c is equal to 0. If we were to try to satisfy the last condition, we would say b over 6 plus 8c over 6 equals 0. We're not going to be able to get that, but that's the next thing on our wish list, so I'm just going to write it there so you know what the technique is up to. Okay, you just take these coefficients, and again, they're all going to be zeros, except in the one case where we're trying to wipe out the h squared, so that all that's left is f prime. So these terms we would like to get rid of, those terms we would like to get rid of, but they're actually going to turn into our error terms. Okay, so we generally get 3 equations, 3 unknowns, and then this is on our wish list. And so let's go ahead and solve for that. Actually, you go ahead and solve for that. I'll wait for you. Okay, so if you just take this equation and solve for b, that equation and that equation, you can solve for b and c. And then you go through and you lastly satisfy a plus b plus c, and I'll let you do that yourself. And then a ends up being minus 3 over 2h. Okay, so these pieces over here, we had hoped that we'd be able to satisfy them, but we can't satisfy this last condition, and so instead we kind of think about these x's as becoming c's, because that's going to tell us what our error term is. So that's kind of what happens there. Let's put all these pieces together now. Okay, so you just literally pull all that stuff together, do a little algebra to pull out the 1 over h's. In fact, I just pull 1 out of 1 over 2h. So actually, I just rewrite this as 4 over 2h so that everything's the same. And then there's this little piece, f triple prime c h cubed, but I'm not going to put a coefficient in front of it. I just want you to know that's the order of that error term. Okay, so it's something like that. All right, so this is what we call a 3-point formula. And we have already talked about the fact that there's another 3-point formula which only uses 2 points. So the point is, if you do this, and I encourage you to do this, like pause the video and do it, if you work out A, B, and C in the following situation, if you say f prime of x is a times f of x minus h plus b times f of x plus c times f of x plus h, and you do exactly the same thing that we did just before, but now with the different center, then what you should find is A and C will be balanced. Okay, so one will be like positive and one will be negative, but B is going to be 0. So again, A and C will be equal in magnitude, B will be 0, but the reason why we're calling it a 3-point formula is not because we're using 3 points, but we had 3 points to start with, even though we ended up giving one of them a weight of 0. So this is a 3-point formula, and you should work that out. And then the other point is that if you work out f prime of x is approximately a of f x minus 2h, b f of x minus h, and c f of x, this would actually be a waste of your time, because it's exactly the same as the 3-point formula we did with f of x being the first term, because we've just got now the mirror image of this. So in your homework, I ask you to evaluate or to find out the 5-point formula that's, I think, centered at the center. And so you can use symmetry. If you know that it's a 5-point formula and it's centered in the middle, that middle term is obviously going to be 0 due to symmetry. And then, so if you have 5 points you sample, this one's going to be 0. Whatever this one is, that's going to be the opposite. Whatever this is, this one's going to be the opposite. So you can take advantage of that symmetry in your homework as a shortcut, and that's totally fine. Okay? All right, so we're not going to do an integration exercise today. We'll probably do one later in the semester when we talk about other quadrature methods. But these same techniques can be used to optimize integration techniques, where you just write out the Taylor polynomial and then you find the coefficients that make everything work out. So that sort of wraps up those examples for now, and we're going to move on to Richardson and extrapolation. And you can use Richardson's extrapolation with things such as numerical integration, which we're going to be doing, I believe, in the next chapter. Okay, so this is a way to accelerate. This is essentially an accelerating technique combined with some kind of other thing that's going on. Okay, so here's the context. So this is pretty high level. I don't have an actual exercise, but don't worry, we will. But I want you to just see this high level discussion. What we're looking for is m, and what we have is n. Okay, so what we want, something, and what we have some kind of expression that's an approximation to m, but it has an error in it, and the error changes when h changes. So it's some function of whatever. Okay, so we have an error. But this is the actual approximation. So let's see what the error term looks like. Let's pretend that we can expand our error as a function of h and that it's a polynomial. This is rather clever. This is a rather reasonable thing to do, because we just said that basically any smooth function can be expanded as a Taylor polynomial. Well, let's see if our error term can. Error in n of h, approximation. Okay? And so we think it's some kind of Maclaurin-like thing. Presumably you can't make h equals 0 because that is a subsize. Okay, we have two flavors of this situation. I'm not going to derive both of them, but the two flavors. One is the one that's here, where you have h h squared, h cubed. All of the terms come into play, and then there's the evens only, and it changes the formula. So just be aware. There's two flavors, and you'll have to deal with both of the flavors in your homework. Okay, so just be sure to keep them apart. Okay, so let's go back to the discussion. If we have, so we have this expression, and one thing we might want to do is then the same thing, you're gonna do the same thing, but you're gonna do it with h over 2. So how is this going to change? If I take all my h's and replace them with h over 2, how is this going to change? Well, h over 2, h over 2, h over 4, and h over 8, because I'm not going to put it in parentheses. I'm going to leave it hanging out there. Okay. There you go. So is there any way we could solve for something and get rid of something? We want to get rid of the k1h error term, and hopefully we just have the k2h squared type pieces. So what I'm going to do is I'm going to multiply this by 2 to give me something, so that I can subtract one copy of this. Okay, your standard technique, right? So I'm going to just figure out what this looks like when I multiply by 2. So it's going to be 2m minus 2n h over 2 is k1h. We did this so that we could subtract, so don't be too surprised about that one. k2h squared over 2 plus k3h cubed over 4, and so on and so forth. Okay, now I'm going to take this guy and subtract this guy. Okay, I'm going to subtract, and I'm going to get m minus, so let's say plus nh minus 2nh over 2. And then, as intended, these guys cancel out, but nothing else is going to cancel out, right? You're going to get, since it's the bottom one minus the top one, it's going to be negative, minus k2 h squared over and so forth. Okay? So what we're going to do, I'm going to just have to resize this screen. Hold on. Okay. So what we're going to do is we're going to label some of these parts. This part I'm going to, first of all, I'm going to chuck onto the other side, so it's going to switch the order of this. And I'm going to call that something. Okay, so m is equal to 2n h over 2 minus n of h, and then I'm going to just take this stuff chuck it down here. It's still there. Alright, and so these pieces here I'm going to call n2 of h. So we had n of h. N of h is now going to be called n1 of h, so we don't get confused. Well, we're going to do this whole same thing again, but now we're going to use n2 of h and n2 of h over 2. Okay, so I'm going to put this over here, and I'm going to put another copy of it. So we're going to replace h with h over 2. So h over 2 becomes h over 4. I'm still using regular old n, which is n1. H squared over 2 becomes h over 2 squared over 2, so that becomes h squared over 8. H over 2 cubed over 4 becomes h cubed over 8 over 4. So that's going to be like over 32, I guess. Yeah. Okay, what a pain, right? These terms are getting really small. No, but that's good. That's good. We want them to get very, very small. Okay, so to solve for m, what we're going to do is we're going to multiply this guy by -1, meaning we're going to subtract that guy. This guy we're going to multiply by 4. Is that going to do what we want? Because we're going to try to get rid of the k2 term. That's the one because we already got rid of the k1 term. So let's try that. So what we're going to do is it's going to knock out those two terms, and we're going to say 3m, like I'm just going to relabel these guys. This piece I'm going to call n2 of h over n of h These are both n2s, but this is n2 of h over 2, and then this should be n2 of h. Okay? Okay, so what we get is we're going to get 3m on the left, and we're going to get 4n2 of h over 2, and we're going to get minus n2 of h, and then we're going to get k3 h cubed terms coming down, and you can only do so much. Okay, so we're going to solve for m, and then we're going to get n2 h over 2 times 4 minus n2h, and all that is going to be over 3, if I can get my line straight. Okay. So the way they write this in the textbook, and the way that I really hate this, but this is what they do. It ends up actually, after you see why, it makes total sense. So you end up saying n3 is equal to n2 of h over 2. So they factor out a whole copy of this, so they get rid of 3 n2s over 3, and then they write this fraction. But it actually helps you see how it's converging. It makes you feel more like it's a fixed point method, which it kind of isn't. Well, it is, I guess. It's going somewhere. Okay. So this kind of thing keeps repeating. You keep doing this, you keep saying, well, now that we have a new expression in terms of h, we're going to just keep wiping out term after term after term, and you can go ridiculous with this. And what we end up with, okay, so this is what you end up with. You can get sick of this or you can enjoy it, but this is the repeated sequence, and that's why they factored out n2 and then said n2, plus or minus the other piece. And this is all because it all just makes sense in context now. Okay, so this is for errors that look like this: h squared, h cubed, all the error pieces. But what we're going to have, one of the two homework questions is going to be the alternate form. This is when you have the error terms that are only even. So you're going to have special only even error terms, so we can accelerate that thing even faster. And so it's a very slight difference in the formula, but it makes a huge difference. So if you're trying to get the right answer on the homework and you're using the wrong one, you're still going to converge, and you're going to say, this is really, really close. Why is this not working? And that's why, because you got to really pay attention whether your error terms, and the problem will tell you. I tell you straight out. So anyway. Okay, now time for a different kind of example. Okay, so this is only slightly less abstract. So slightly more concrete for you. Okay, but it's still fairly abstract. But this is going to be an evens only example, right? Because the first error term that comes out is an h squared. So let's set this up. Okay, so we know this. Richardson says this. So how do we make use of this guy in Richardson, right? Okay, here's what's going on. What we want and what we have. Go back to that bit. What we want is f prime at 0. What we have is f at minus 1, f of minus 1/2, f of minus 1/4. We don't actually have f at 0, but we could, but it's not actually relevant because we're going to use this technique that doesn't use it. But let's say we have this information. They're not equally spaced. No, they're not equally spaced. And this may be very well the type of thing where Hamming would yell at the whole community because this is just a mathematical construct, and when are you ever going to sample a function like that? I don't know. So this could very well be just one of these beautiful mathematical things that is of no practical value. But let's go ahead and investigate it. Okay, so what we want to do is figure out what n1 is. n1 is of 1, and then it's whatever you want to calculate it, f of 1 minus f of minus 1 over 2. And 1 of 1/2 is going to be f of 1/2 minus f of negative 1/2 divided by, well, what are we going to divide by? 2? No, we're going to divide by 1. So what's the point of that? And then n1 of 1/4 is f of 1/4 minus f of minus 1/4 and divide by 1/2. Okay? So then what are you going to do? Well, then you're going to take that, and the Richardson says n2 of 1 is going to be n1 of 1/2 plus n1 of 1/2. And then this is not hard to code. This is hard to derive, but it's already derived. So it's just a fun programming exercise now. n1 of 1/4 minus n1 of 1/2 all over 3. Okay? Now, since we started with 3 n1s, we get 2 n2s, and we get 1 n3. So finally, we're going to figure out what n3 is n2 of 1/2 plus n2 of 1/2 minus n2 of 1 all over 15. Okay? So we can try this. Okay, let's try this. We're going to, well, first of all, we just know the particular integral, it goes to 1. We're just going to integrate sine of x and, okay, or cosine of x or something like that. So let's go ahead and do this. From math import star. Okay, I just wanted to look up what this function is before I show you it converging. Okay, so we want derivative of sine of x at x equals 0. We know it's equal to 1. Okay, so that's what we want. You can verify that, but this is what we're trying to do numerically to demonstrate. So capital A is going to be n1 of 1, so I'm just going to say n1 of 1 is equal to sine of 0.1 minus sine of negative 0.1. So my first h is just going to be 0.1, and I'm going to divide by 0.2. Okay, n1 of a half is equal to sine of 0.05 minus sine of negative 0.05 divided by 0.1. So what does n11 look like? n1 half look like this. I clearly did this wrong. Oh, because I forgot a 0. That was ridiculous. That looks better. Okay, now let's try n1 of a quarter. Sine of 0.025 minus sine of negative 0.025, and then I'm going to divide that by 0.05. That looks good. Now n21 is going to be n1 half plus n1 half minus n1 1, and that's going to be divided by 3, right? That worked. And then n2 half is n1 quarter minus n1 quarter minus n half over 3. Alright, it's getting closer to 1. Now we're going to do a single n3 round. So what does n3 look like? n3 1 is n2 half plus n2 half minus n2 quarter. But now this turns into a 15. I'm going to just double check that this makes sense, because I use different variables in my notes. Okay, n31 is n2 half plus n2 half minus n2. There's no such thing as n2 quarter. It was an n21. Okay, there we go. Okay, and there we see it's very, very close to 1, and we only started off with sine of 0.1, sine of negative 0.1, sine of 0.05, sine of negative 0.05, sine of 0.025, and sine of negative 0.025. Okay, and so that would be how you manage that. Okay, hopefully that made sense to you. If not, rewind the video and watch again. What you want to do, if this is confusing, is type it out yourself as I type it out and see how each piece fits together. All right, hopefully that works for you. See you next time.